Hi class, I'm Shubhrose, and me and Deon are going to be presenting on the topic of financial applications for parallel and distributed systems. So I'll start by first explaining the problems in finance that will actually benefit from a parallel architecture. I'll then move on to explaining some important terms that we'll need later. And then finally, I'll explain the algorithm and its efficiencies. So to start off with, let me explain the problem. And to do that, you need to understand what a financial derivative is. So we can think of a derivative as a contract between two parties. And the value of this derivative is based on the underlying financial assets. So these are some common underlying instruments that include bonds, stocks, commodities, currencies, interest rates, market indexes. And this whole field of studying derivatives is quickly evolving. And there exist models for forecasting, so kind of determining the future price of a derivative. And if you know the future price of a derivative, you can make smarter decisions and hopefully end up making a profit. The problem is that when dealing with financial derivatives, it usually leads to large non-linear problems. And these problems need to be solved within a certain amount of time. So that's where the bottleneck is, and that's where parallel algorithms come into play. The portfolio management problem is the main problem that we'll focus on. So in this problem, an important aspect is that an investor can choose from many assets over many dates. And these assets that they put into their portfolio, their prices are determined by just market dynamics. And the investor's overall budget is determined by the price of the goods and the financial securities that the investor purchases. So you can probably tell that this leads to large computational requirements, and these requirements increase when there's problems with trading or market frictions. The goal of the investor with their portfolio is usually to minimize their risks associated with their portfolio. So they want to minimize their risk while also maximizing their return. To solve this, there's been mathematical models created for managing portfolios. So an important model that many others derive from is the Markowitz mean variance optimization model. This is kind of a framework for assembling a portfolio. And it's a way of, and its expected return is maximized for a given level of risk. So the investor chooses a risk, and this model will give them the maximum return. So it is kind of a formal way of extending diversification in investing, which is the idea that owning different kinds of financial assets is less risky than owning just one type. And the key insight of the Markowitz model is that an asset's risks and return shouldn't be assessed by itself, but it should be assessed by how it contributes to an overall risk, a portfolio's overall risk and return. The next model is the Black-Scholes model for options pricing. And it's also an important model used for risk management. It takes in 5 input variables: the strike price of an option. So that's the price that you purchase the option, the current stock price, the time of expiration, the risk-free interest rate, and the volatility. And this formula has demonstrated an ability to yield prices close to the observed market prices. So that's why it's useful. So there's lots of models for helping us price derivatives without actually being an obvious way of implementing them. So this paper by Rupa et al., it worked on implementing these models towards solving the portfolio optimization problem. To find the solution for these problems, there's a need for efficient algorithms, and that's where parallel algorithms come into play, where we will use them to price a class of multi-dimensional financial derivatives. Multi-dimensional just meaning there's many underlying assets in this derivative. So now let's move on to the relevant terms. So we'll start with options. So an option is a term interchangeable with derivative. Let me actually turn this off. Yeah, so we'll start with a call option. So a call option is basically a contract between the buyer and the seller that gives the right to the holder to buy an asset at a predetermined price. The holder doesn't necessarily have to buy it, they just have a right to. And the option is created for usually a specified amount of time, let's say 6 months or 12 months. If an option can only be exercised at its expiration date, meaning you can only purchase the underlying asset at the end of the life of the option, this is called a European option. And if the call option can be exercised any time before its maturity, then it's called an American call option. So an example of this, or the way I would like to think of it, is that if I have a European call option to buy a stock in 6 months for $1, I will buy the stock only when my option has matured. By purchasing the call option, the idea is that I'm hoping that the market price of the stock is higher than the price stated by the option. So this lets me just sell the stock in market at a higher price, which leads to an obvious profit. If I have an American call option to buy the stock, I can buy it at that price anytime between now and the 6 months. Now, a put option gives its holder the right to sell a pre-specified underlying asset at a predetermined price. So call is buy, put is sell. The holder doesn't have to sell like before, but they have the option to. And similarly, if the underlying asset can only be sold at the end of the life, it's a European put option. And if it can be sold anytime between now and the end of the option, it's called an American put option. So another example we could think of is if I have a put option for a stock in 6 months, where I have the right to sell it for $2. And if the stock costs $1 in 6 months, I can simply buy a stock and sell it for the $2 and make a $1 profit. But the problem is, if the stock actually is $3 in 6 months, that means in the market, its price increase. I would simply just choose not to sell and lose the money that I spent on the contracts. So options like these can be written for many underlying assets such as equity, precious metals, and stocks. And the person who writes the option must buy or sell to the holder at the contract price. There's many factors that influence the pricing of an option. These include strike price, like we said, and strike price. And strike price again is the price at which a put or call option can be exercised. The volatility, the risk-free interest rate, and a current value of the underlying asset. And here we described the Black-Scholes model that we had before. It simply just requires the 5 inputs and is a differential equation used widely to price option contracts. Now we're going to implement this Black-Scholes model using parallel algorithms. So now let's move on to the parallel pricing algorithms. So I'll describe parallel pricing algorithms for options first with just a single asset, so a single stock. They approximate the Black-Scholes mathematical model, and they do this by representing the asset price movement in a lattice. So this is how I'll try to break it down. So this is a one-step binomial lattice. We can see at A, we have a strike price of 20, and this is where the price that the call or put option can be exercised, that's 20, which will either go up to B or it'll go down to C after some time T. And this is the profit that we could potentially make if the price goes up. Now we apply this technique to a multi-step binary tree. So here we can see that there are 4 possible stock prices after some time T. And over the 2 sub-intervals we have here, the asset price is assumed to either move from S to SU, where it goes up, or S to SD, where it goes down. And the probability that this happens is P and 1 minus P. Here, this is a non-recombining tree because these 2 values, the SU, SUD, and the SDU, are not equal. So these are 2 separate nodes. If we had a recombining lattice, we would make sure that these 2 are the same, but we're not doing that now. We're just assuming they're separate nodes. So constructing the lattice like this recursively has been proven by Holt et al. To approximate the continuous time risk neutralized process for asset prices. So now the recursive algorithm proceeds in 2 phases. We first construct the lattice, and then second, we work backwards through the lattice from time T so that we can compute the present value of the option. So the binomial lattice can first be computed by dividing the time interval we have from 0 to T into L smaller intervals. It was shown by a paper by Wilmot et al. That if we then set up the U, D, and P values in such a way that the mean and variance of the asset price movements will match the mean and variance of the continuous time risk neutralized asset price. Now for the second phase of the algorithm, this is where we work backwards from the leaf nodes at the time T to compute the option price. At time T and leaf node I, so this is node I, and at time T, we know that the value of this option is either 0, so this is where we don't do anything, or we don't exercise the option, or it is the strike price K minus the current price of the asset SI. Now, if we move on to T minus 1, so moving to the left in the lattice, and with node J, the value of the option is the greater of these 2 values. So the 2 values are the current asset price greater of the, so no, this is the immediate exercise of the option. So we're doing the strike price minus the current price. Or now this side is the expected value of the option where we hold for another time period. So now we're at T minus 1. If we hold for another time period, then we will have this output. This one-step option pricing formula can be applied to each of the steps in computing the option value and have been extended to a multi-step lattice using the above formula. So these formula work for a multi-step lattice as well. Okay, so now we'll actually move on to how processors are distributed in this algorithm. So if we let P be the number of processors, in the recursive algorithm, we'll first delegate processor 0 as the master processor. We start the first processor at the first level, which corresponds to time equals 0. We build a non-recombining tree until the number of leaf nodes equals the number of available processors. Each leaf node is assigned to a distinct processor, and then each processor starts building its own tree, working independently in their subtree. As soon as a processor creates a tree with a certain depth, here is L minus log 2 of P, it starts working backwards and computes option prices in every node. And at the end of the computation, each processor sends its final value to the master processor, which then computes the option value at time t equals 0. So here's the problem with this algorithm. So the recursive non-recombining algorithm, like we saw, it creates 2 to the L nodes. So 2 to the power of the number of levels in our lattice nodes. This actually restricts its usefulness to only short-dated options. So options that have a time that's more recent. To accurately price options with long times to expiration, this algorithm is obviously not efficient. So now we'll focus on instead creating a recombining tree that reduces the number of nodes by making sure that these two values, SUD and SDU, are equal. For the recombining algorithm, we'll assume that the number of levels and the number of processors are powers of 2. So here we have 4 processors, it's a power of 2, and the number of levels is 8, is also a power of 2. The number of leaf nodes is the number of levels plus 1. So there's 9 leaf nodes, there's 8 levels, and all the leaf nodes are evenly distributed among the processors, but the last processor receives an additional node. So each of them have 2 except P3, which has 3. Every leaf node here calculates the option price as the local payoff at these nodes. Every processor I sends the value of its boundary node to processor I minus 1. In a given processor, for every pair of adjacent nodes at level I, the processor computes the option price for the pair's parent node. The computation then proceeds to the previous level, or level I minus 1, and eventually processor 0 computes the option price at the level L equals 0. So at each time step t, the algorithm operates in 2 modes simultaneously, communication and computation. In the communication mode, adjacent processors exchange data on option values. So that would mean that P3 would send the value of this node to P2. And then P2 would send the value of this node to here. P1 would send the value of this node to here. And then eventually processor 0, so this way P0 only receives from P1. P0 is not going to send to anyone. And then eventually the processor computes the option price for the pair's parent node. So this processor is going to compute this parent node. And this processor is also going to compute the value of this parent node. And eventually we can see P0 is going to go all the way down and get to 0. Now, so the authors that wrote this algorithm, they actually extended it to handle derivatives with many underlying assets and used that multi-asset and saw that the multi-asset derivatives offered a better problem for parallel computation. I know this is kind of blurry, but we can see that as the numbers of processors increased using this algorithm, the execution time decreased. And as the number of assets increased, the processors with the higher number of processors did not increase in execution time as much. This is very important for the financial industry since long-dated derivatives and many underlying assets are common in practice. And so these will actually work for long-dated derivatives with many underlying assets. I'll now send it to Deon.
Hello everybody, my name is Deon Seyfi and I will be talking about the purpose of these parallel systems and financial purposes. I will talk about the Monte Carlo simulation, the different forms of decomposition, and I will go over an implementation of the Monte Carlo simulation. So the purpose of these parallel systems. Large-scale financial planning requires a combined approach of modeling techniques, algorithms, and high-performance computing. This allows a reduction of modeling errors, improved reliability, and higher representation of profit potential. Shorter computation times allow previous intraceable problems to be really tractable. Um, there are normal use cases such as asset pricing, optimization problems, creating programming support to each of these programs, and the other more complex models for faster computation. One of the main benefits and purposes of having parallel systems within financial algorithms, financial systems, anything financial, is mainly to have an upper edge on the other trader or other computer that they're going competing against. Because in the end of the day, markets is purely based on who is either first or making the smartest moves at the moment. And there's no really other way around it unless you are technically cheating or doing something illegal. So, um, yeah, that's why you would need these parallel systems for financial markets. Now, next slide. So now we'll talk about the Aurora financial management system. It is currently a decision support tool for portfolio and asset liability management. An investor is able to choose a portfolio of various assets where the investment becomes risk adjusted, developed with a framework of it is developed with a framework of stochastic and dynamic optimization methods and models. Um, there are two different models being computed to ensure that the end optimization creates a decision for the investor. So I will talk about the financial management system, and I will run base of how it currently computes and makes its optimization. So you have its first financial market generation, where number one, it takes in current market interest rates and stock indices based on the times of each of these prices and interest rates, and it becomes one of the inputs of through an asset performance scenario tree. You have number two, a liability scenario generation, where it takes in information such as history of pensions and contributions, mortality and other statistics, and accounting rules. You will be taking these scenarios because the market is um, based on one of the investing purposes of the market is the constant investment and retirement investment of our 401ks, Roth IRA, pensions, and everything like that. Um, most of these accounts and all the retirement accounts will be benefiting from the newer developed retirement accounts that are continuously buying within the future, and they develop their scenario trees of uh, liabilities. So then you take this stochastic optimization model generation, and it also takes in any legal and investment constraints. Where I talked about, um, you there are legal things that illegal things you can't do. Um, so from that point on, it starts to optimize the problem, and then it creates this optimization at step 4. So now we will talk about the Monte Carlo simulation. Um, it is a continuous time of stochastic process and is constantly represented uh, using the Monte Carlo simulation. Each path is built by using random variables based on the samples that are drawn by a random generator. These paths are based on interest rate lattice and allows for more efficient sampling and procedure. So to talk more in depth of the Monte Carlo simulation, it is basically you start from a single node and you start to develop your random variables or random paths that would possibly happen. And you start to compute based on these random paths. So for every Monte Carlo simulation, in the financial aspect, we start to simulate um, different price changes and different scenarios and different um, economic changes and all these type of things that could affect an asset price. So you take all those into account and you start to generate different paths. And then from each new path, you start to develop new and newer paths based on random generations. And then you get your final answer towards the end um, at the final node based on the time that you're trying to reach. So now we'll talk about the algorithm of the Monte Carlo algorithm. So you select a different number of possible paths, n. So as we talked about, it's just all the number of paths where 1 is less than I and less than n, where I is the uh, specific number of path, is a specified number of path between the nodes. Each path will correspond to a future scenario based on the interest rates. So in this Monte Carlo simulation situation, we will predict scenarios based on what will affect interest rates, and we'll calculate the asset price based on each scenario. So then we will apply the formula at each scenario node. So PV is present value equals the sum of all the costs, and it is and also including the interest rates of time over time. The sum of all these price values would then be averaged out by the number of possible scenarios, creating an estimate prices of the instrument. So then at that point, you take all the total, you sum up of all the total possible price values, and you divide it by the possible number of paths that were produced. And from there, you get your estimated value or estimated value of you get your estimated value of the instrument. Could be a stock, bond, interest rate, anything that you're specifying trying to calculate. So now we will talk about backward induction. In order to make the predictions more accurate and to save computation, um, using backwards induction, their paths are not selected at random. They're instead used in a deterministic manner. So there are a total of m cubed paths from the root node to the final node, and each path has its independent cash flow. Computers and the price value are recursively applied to the scheme at each node, and each state of the node carries future information for further nodes, which allows it to be propagated in backward time. The backward induction on a mean lattice has a time complexity of O of m, which allows for linear time. So now that we're gonna apply we're gonna talk about the backward induction and represent it. As we will see here, um, we have we okay. So we start at time 0, and we end up at time 1, 2, 3, 4, 5 as shown in the graph. So at time 0, we start at around less than 0.04, and we start to move forward. And as you can see, as represented and talked about previously, each it becomes n. It starts to become n cubed. So that's the number of possible paths. So for each one, you start to produce 3 different paths, m cubed. So moving forward, we start from this node and we start at 1, we end up at about 0.07 and then 0.8 and then 0.10. And for each node, it communicates through further passing information to help represent further information. So yeah. And in a Monte Carlo simulation, it will be a lot more cluttered, as in this representation of backward induction, we decide which path we want to take, which allows less of a computation time. In the Monte Carlo, is purely at random and purely produces a lot of possible scenarios, which will take a lot more computation time. So we're going to talk about model decomposition. Model decomposition exploits the structure of a problem where the optimized problem in a set is set in a linear way. It allows for solving a set of sorry about that. It allows for solving a set of smaller subproblems to optimize the components of the problem. The subproblems are coordinated by a head or master processor, which produces estimates of the solution. It will be discussed of 2 different forms, two-stage decomposition and nested Bender's decomposition. And this is where we start to go into the parallel processing of how these things are computed. So two-stage decomposition. In a two-stage decomposition, the second stage decomposes into a sum of local objective functions with all the succession nodes, and the root node uses each succession node n to solve its local problems while taking into account of the master solution. In each iteration, the master node minimizes its sends to the slaves and receives constraints from each sub-node to improve the solution in the next iteration. So as you can see in the graph here, you will have your master node, and it produces nodes in a straight line, kind of like a daisy chain. Each sub node is talked to by the master node, and through every iteration, the data from the subnodes goes to the master, and then the master sends it back out to the next new iteration or the next new subnode that is used to find a more accurate solution. So now we will talk about nested Bender's decomposition. The decomposition principle can be applied to also a multi-stage tree-structured problem. Each node acts both as a master and a slave. Only leaf nodes are slaves. Each iteration is performed by the master and the slave node, and it has a set step-by-step process it follows. In this multi-stage nested Bender's decomposition, takes the form of a tree data structure. It can also kind of be a graph, but mostly it will probably be developed as a tree data structure. So we'll talk about the steps of this nested Bender's decomposition. for each step, it will have either a slave or master next to it to dictate which processor does what. So we'll start at step 0. Let I equals 0, and you set the approximation of the value function and set feasibility constraints, meaning that you start to initialize the function and its values that will be needed to be taken as input for to solve to compute the problem. So at step 1, we have the slave node, and this node receives a solution calculated by the master in iteration I or any iteration prior, and the current approximation from the master node. So the slave receives the data from the master node, and the master node at step 1 receives cuts from the slave nodes. So they are both at step 1 passing information to other nodes. Then at step 2, these nodes solve the local problem that it is trying to solve at the moment. At step 3, the master node, if the problem is feasible, the node sends a solution to all the other slave nodes. And at step 3, the slave node, if the problem is feasible, the node compares the objective value with the master approximation. So all the nodes start to communicate with their solutions and start to compare if it compares to the objective value. And at the meantime, once the comparison happens, there's one of 3 scenarios that happen during the slave node. One of 3 scenarios happens. So at step 3.1, if the approximation is correct, the master node is notified and the signal is cut. At step 3.2, otherwise, if not correct, the hyperplane is calculated and sent to the master as optimally cut. The constraint will improve the master's solution. And at step 3.3, if the problem is infeasible, a new constraint is sent to the master to be calculated, and it is also sent as a feasible cut to the master. So at that point, we move to step 4, where you start to increment I by 1, and then you return back to step 1, and you start to reassign data to slave and master nodes and start to have new calculations from that point on. So now we will talk about, we will go through an implementation of the Monte Carlo simulation. So the Monte Carlo simulation is created by using a graph data structure. Each node data type is based with pointers, where each succession node has its own computation. All successor nodes are computed at each step until each final nodes are achieved. So I have written an example of how this graph data structure would look like for a Monte Carlo simulation. So you'll have its class defined as a instrument. So it will just define its instrument type. So basically saying what kind of asset we're trading or what we're calculating for basic knowledge of that data structure. We will store the number of possible paths of this graph. We will store the number of paths that were selected, and then we will store the specified prices of the each calculations. So we will initialize, so then the algorithm will work as so. I will equal 1, and then you have its selected paths that it's followed. And then path will equal a random path, so you select the path starting at the root node. And then discount the cash flow to time using the discount factors to the path. So you start to calculate the price of that node, where you start to consider its cash flow and all the factors that take place of the path. And then from that point on, after each of those node calculations, the end of the at the end of all these node calculations, you start to retrieve all the possible prices, and you get the sum as noted, and you divide it by the number of paths that is taken to reach that endpoint. And that is the end of our presentation. Thank you. If you have any questions, please ask in the discussion board. And thank you.